MC Jordan, and I will be presenting Physics 2211 Lab 2, Motion of a Falling Object. The purpose of this lab is to observe and analyze the movement of an object dropped vertically towards the ground from a resting position. We will be exploring three main principles in this lab. Newton's second law, which is the idea that an object acceleration is dependent on the forces acting upon it, which will be utilized by iterating the position and velocity of the moving object. This will be done by using the velocity update and position update formulas seen here. Next, we will be using the gravitational force, which is the acceleration due to gravity of an object near Earth's surface. Due to the fact that we are near Earth's surface, our mass will be negligible enough to simply declare gravity's acceleration to equal 9.8 meters per second squared. Moreover, this gravity constant will be used in conjunction with the object's mass to create a weight force, which is the vector form that can be seen here. Finally, we will look at the drag force, which is the force opposite to that of the gravity force due to the air particles that are hitting the falling object. This force is declared by the drag constant times the square of the magnitude of velocity. The vector form can be seen here as well. The objective of this lab is to see the motion of our falling object and compare it to two computational models, one without drag force and one with drag force. We can expect to see all three models from a following trend of positional movement, which is downwards and increasing as it goes down through time. And for this experiment, I have declared the object as the system, which is a balled up cotton ball, and the surroundings as the external force on the object, that being air resistance, gravity as well. We can also assume that the object is moving in the negative y direction and that it's not moving in any axial directions besides the y. Here is the tracker model and the graph that was created after dropping the object. The shape of the graph is accurate to what is expected as the acceleration of gravity is causing the change in position to increase in the negative direction. Here's some data that was gathered from the tracker model. The video was shot in 30 FPS, so we have our time set per frame as 1/30 or 0.033 seconds per frame. The initial time, position, and velocity have been set to approximately 0 to simulate the object's start at rest. Time of the motion was about 0.467 seconds, and the mass of the cotton ball was weighed at 0.053 grams or 0.00053 kilograms for SI units. Using the data found from the tracker model, I have input this into the computational model seen here. For the iteration conditions, I have used the principles discussed prior in the coded context. The main part of this iteration is the way the net force is derived by using the weight force plus the drag force. Because we want to create a model without considering drag, we need to set the drag coefficient to 0, which can be seen in red. And this will cause the weight force to be only the one accounted for in the object's falling. Next, when creating a model with drag, we can use the exact same conditions as the prior model, except we change the drag coefficient to a non-zero number. This is found based on the object's mass, and for my experiment, I got a drag coefficient of 0.00015. After running both models, we see how they both compare. The position time graphs are similar, however, the drag force is expected to be more accurate to that of the observed model. The visual also shows the forces as arrows, where the orange arrow is the gravitational force and the blue arrow is the drag force. Putting all the models into one graph, we see that initially all the models have comparable changes in position. However, they start to taper off from one another, specifically showing that the computational models overestimate the changes in position midway through the job. We also see that the model without drag has a greater change in position at the end of the fall, while the model with drag is comparable to that of the observed model. Some possible sources of error is rounding errors that could slightly skew each point, distortion of the tracker video, which could show inaccuracies when changing in position and putting each point mass as the object falls. And we could have a slightly inaccurate drag coefficient, which may not be the same as the observed model. In terms of predicting the terminal velocity, which is the velocity that is reached when the drag force and the gravity force are equal to each other, we can make a good assumption as to what it will be by finding where the slope equals 0 on the velocity time graph of the model with drag. Based on the graph, it seems that the object will reach terminal velocity at around -5 meters per second. Now let's say instead of the object starting with rest, we throw the object downwards. Will the terminal velocity be the same? And the answer to this is yes. By changing the initial conditions to have a different initial velocity, we see that the graph is similar to when it started at rest, with the only change being when the graph starts at t equals 0. Not only that, but the graph reaches an asymptote at the same velocity as the previous model. We can therefore conclude that the terminal velocity will be the same regardless of the initial condition, but will only reach terminal velocity sooner if it was thrown downwards. That is the end of this presentation. Thank you for listening.